Alright, we're comparing and contrasting the differences between a ball sitting on the ground and a positively charged particle sitting on a negatively charged plate. Well, if we recall from long ago with our first physics course, we know that like all matter, our ball is going to have a mass m. We always, the Earth is so large, we would always consider things a flat plane, and we consider that our gravity field would always go in just it would accelerate in just the vertical direction, because we can consider the plane here to be go infinitely outward, and so we know that we would calculate our weight of the object, our force, as force equals mass times acceleration. Alright, so assuming, let's say we have a 1 kilogram mass, we know that because of the size of the Earth, we're going to later contrast that to like the charge of this plate here, but okay, the size of the Earth, we would end up with our acceleration to be 9.8 meters per second squared. So, you'd have, like, let's say 9.8 newtons was equal to 1 kilogram mass times 9.8 meters per second squared. Alright? And likewise, then we would talk about energy. You have your total energy is equal to your kinetic plus, that should be capital K, kinetic plus your potential. We would always, for just basic formulas like this, a static object, the potential was, the kinetic was 0 because it was static, alright? So we'll look at it from that perspective. And then this right here, our potential, was the mass times the acceleration times the distance between them, or more frequently you'll see it mgh. Alright, so that's how we calculate potential energy over here. Looking over at our positively charged particle, which is attracted to the negatively charged plate, we're going to consider this plate to be infinitely large. Alright, because that's what we're generally speaking in terms of for these problems when we talk about a charged plate and a very, very tiny proton floating around on it there. So, we would look at our electric field, because this is infinitely large. The area is infinitely great. It's essentially a vertical E field. Okay, goes just straight down. So we could calculate that based on the charge density of our plane here. I don't know if you guys recall, the E field of a plane is equal to the charge density over 2 epsilon naught, which is also the same as charge density times 2 pi and our K constant. It's easier for me to remember that one. And if you notice, we neglect distance the same way we tend to neglect distance from the acceleration of gravity, and that just has to do with, since it's infinitely large, the distance doesn't really have an effect. It's just a constant value, which is explained in a previous chapter. So likewise, actually, we can calculate the potential energy if this is a non-moving object. Let's say it's up here, okay, at a distance. We tend to use r for distance in these problems. We can use our potential energy is equal to the E field, okay, that's our acceleration, times the Q, which we can kind of compare to the mass, okay, the charge of this, okay, let's say a positive charge of that guy, times our r, our distance. Alright? So that's how we would compare the energy of a ball, depending on its height from the ground, versus the E field times the charge of our particle with its distance from the infinitely large plane. Yeah, I guess that in a nutshell is the comparison of those two.